So now let us go to the next set of conditions. So the fourth condition is if both roots are greater than a given number k. If both roots are greater than a given number k, then what is the condition? That means if you take the graph, assume that k is some number. K can be 2, 3, minus 2, minus 1, so on. So if both roots have to be greater than k, that means the graph has to lie something like this. That is, this is one root and this is the next root. So both the roots should be greater than k. Now what is the condition which ensures that this happens? So if both roots have to be greater than k, the first condition is that d has to be greater than or equal to 0. That's a general condition which is always true. Because if both roots are to be greater than k, first the roots have to be real. Next. So what will ensure that both roots are greater than k? The second thing is the x coordinate of the vertex has to be greater than k. The x coordinate of the vertex is nothing but minus b by 2a has to be greater than k. So does this condition ensure that this happens? No. So this will happen if this happens. And what is the third condition? There is one more condition which needs to be valid. So now the vertex lies after k. Now this next condition is that the graph has to rise up before it reached the value of k. That is, f of k has to be greater than 0. F of k has to be greater than 0. So these three conditions do they ensure that both roots are greater than k. So if you carefully observe, it looks so. So discriminant is greater than 0. Minus b by 2a, that is the x coordinate of the vertex, has to be greater than k. It has to lie after k. And before the graph reaches k, it has to rise up. That means f of k is greater than 0. So these three conditions ensure that both the roots of this equation are greater than k, provided you have an upward graph which we assumed. We don't know the graph of this. So the graph of this depends on the sign of a. So assuming that it is an upward graph, if these three conditions are valid, then both the roots will be greater than k. So what we usually do is, whenever a condition like this is given, first we divide the whole equation with a. So you get x square plus b by a times x plus c by a is equal to 0. So first we'll divide the whole equation with a, make the x square coefficient as positive, and now we start our analysis. So discriminant has to be greater than or equal to 0. The condition does not really change anything. So you can apply this in the original equation. And second, minus b by 2a is greater than k. This equation also does not really matter whether you do it for this equation or this equation, because minus b by 2 is the x coordinate of the vertex. Even if it is an upward parabola or a downward parabola, this condition has to happen. So minus b by 2a is greater than k can also be applied to the original equation. The difference is with f of k. F of k cannot be applied to this equation if a is negative. So before applying f of k, divide the whole equation with a, make the leading coefficient positive, and then put x is equal to k. So this is after making the leading coefficient positive. So the first two conditions can be applied directly to the original equation, but the last condition has to be applied only after you make the leading coefficient to be positive. So before applying this, you have to make sure that the leading coefficient is positive. Next, both roots less than k. Both roots less than k. That means how should the graph look like? If this value is k, both roots have to lie less than k. So the conditions are very simple again. Discriminant has to be greater than or equal to 0 because the roots have to be real, and minus b by 2a has to be less than k this time because the x coordinate of the vertex has to be less than k. And the third condition is again f of k has to be greater than 0. This graph has to rise up before it reaches the value of k. So the y value at x is equal to k has to be positive. So again, you need to remember this. Before applying this, you have to make the leading coefficient as positive. So these two conditions can be applied to the original equation. This condition has to be applied only if leading coefficient is positive. So if the leading coefficient is not positive, first we divide the whole equation with the leading coefficient, make x square coefficient as positive, and then apply this condition. Next, the related condition is one root greater than k, one root greater than k, and other less than k. Other less than k. So what are the conditions which ensure this condition? So if this has to happen, then the graph has to be like this. If this is k, the graph has to be like this. I said one root is after k, the other root is before k. So what is the condition which ensures that this happens? So first, discriminant has to be greater than or equal to 0. This time minus b by 2a doesn't really matter. Minus b by 2a can be anywhere. It doesn't really matter whether minus b by 2a is greater than k or less than k. So this condition does not come now. And what do you say about f of k? So f of k has to be less than 0. F of k has to be less than 0. So if these two conditions are valid, then one root will be greater than k and the other root will be less than k. So this can be applied to the original equation. This has to be applied to the transformed equation. The transformed equation means the equation where the leading coefficient is made positive. Because when we got this condition, we assumed that the graph is upward. If the graph is downward, the condition reverses. So it's a general habit that we make the leading coefficient of the graph as positive and then apply the conditions uniformly for all the questions. So this constitutes the second set of formulae. So if both roots greater than k, both roots less than k, and one root greater than k and the other root less than k. So this second set is nothing but a general case of the first set. So the first set deals with both roots positive, means both roots greater than 0, both roots negative, that means both roots less than 0, one root positive, the other root negative, that means one root is greater than 0 and the other root is less than 0. So these three conditions are a general cases for the conditions that we have derived in set 1. So now let us go to the last set.